Hello, I am Dr. Paris von Lockett, and today we're going to be talking about contact algorithms very broadly and how we use those or implement them in SolidWorks. All right, so this lecture focuses broadly on understanding contact algorithms, and like I said, they're used in SolidWorks. In this lecture, our topics are idealized versus real-world contact geometry, which I'll talk about as just a matter of scale, just for your interest and edification. We'll also talk about the difference between what's called augmented Lagrangian and penalty methods. That'll be important for how we do contact in different types of analyses. We'll also talk about contact types in SolidWorks. This is probably the most important part. Three different ones: bonded, no penetration, and the allow penetration type. And then finally, how we assign contact is either global, component contact, or within contact sets. Those are also important. After this lecture, it's important that you're able to discuss the difference between Lagrangian and penalty methods and their applications in SolidWorks, distinguish between correct and incorrect uses of bonded no penetration and allow penetration conditions in SolidWorks. So do you know how to assign the right type? And also, looking at it, can you tell whether or not the type that you've selected is correct? Yeah. And finally, to distinguish between different levels of application of contact in SolidWorks. So when to use global, when to use component, and when to use contact sets. Those are going to be important things as you begin modeling your own types of systems here in the application packet that you're going to be working on this week. We sort of step through it for you, but in the future, when you're doing this on your own, knowing which to use is important. All right, where does this fit? As we've been saying with these lectures, this comes right at the point where we're dealing with a multi-body component with multi-axial stress and stress concentration. So right here, you should be working on this application packet for the plier model, which involves the contact stresses, which are going to occur right there between the plier arms and the fork that it's in touch with. And how we go about applying in SolidWorks the conditions to do that is going to be the focus of today. Or I should say how SolidWorks generally handles contact, and the application packet will take care of how you actually go about doing it. So if you recall, the contact stresses are this complex 3D stress state generated by contact between two bodies. Here we're showing the Hertzian stresses for rolling no slip contact. We have sigma z, sigma x, and sigma y. So we only have our principles. Since there's no slip, there's no shear. These things vary with depth. They're maximized at z equals 0 because these terms here and here go away. But remember, this is an idealized geometry. For this case, we either have two spheres or two cylinders, and they're only in contact in this half radius here for our patch area. This patch area is a circle if these two things are circles, and it is a rectangle if these two things are cylinders. But how accurate is that idealized representation? How big is A? So in the finite element method, though, the size of the scale of the contact is not necessarily important up front, because what the FEA method does is it breaks the surface into small pieces and then analyzes each. So it does this automatically for us. If you're interested in the sort of rudimentaries of how this has gone about, you can pick up this paper by Riggers from 1995, a long time ago. But it lays out in that work a generalized method for if you have some sort of impactor, which has some radius, and if you have some surface, which again has some radius of curvature to it, you can define the interaction between this impactor and this surface in a localized coordinate system of natural coordinates for the FEA method. So if you've had finite element methods or you know something about them, you might recall that FEA tries to break everything down to a regularized normal set of coordinates separate from the global set of coordinates, and then you develop all the equations in this natural coordinate system, and then go back and apply them after transforming those natural coordinates back to your global coordinates. So here is the coordinate system for our natural coordinate patch. We know that somewhere in here we're going to have contact between these two surfaces, and we can actually solve the problem of contact that we're interested in over this domain. Now you know how old this is because they're still calling these masters and slaves, but you know, it was 1995. But even though we can do this automatically, we can break up our body into these discretized little pieces and patches and then analyze contact with respect to those patches, we still have to ask, how closely are we looking at this surface? Because even though we can break it up, do we need to or do we want to? So consider two polished surfaces in contact. What do you expect those contacting surfaces will actually look like? Have a picture of it in your mind for a second. Did you picture this? Here is an atomic force microscopy image of the surface topology of polished glass. Yeah. Notice the units on the axes. Here we have microns, 0 to about 50 microns. On this axis, the same thing, 0 to about 50 microns. Our elevation is in nanometers. So we're seeing here surface roughness of a polished surface of glass down to a nanometer scale. And if we were trying to then look at how ceramics or metals that are equally polished are contacting each other, do we need to get down to this level of refinement? So the answer is no. What happens in the FEA method is that we deal with the idea of contact at a much more gross scale, and really it's a scale on the order of the discretization of the elements that we're dealing with. Remember, the FEA method breaks a body up into small geometric parts, these elements, and then all our analyses are done on those elements. So we're really looking at, if we have two parts and they're discretized into elements, what is the degree of interaction of the surfaces of those individual elements that are in proximity to each other. All right. So what does that look like? Well, here I'm showing two pictures, one on the left, one on the right, of a contact surface and a target surface. These things are discretized into elements. And what happens is we have to use what are called contact algorithms to automate both the search for and computational handling of how these surfaces are interacting with each other. Now, contact algorithms to look at whether surfaces are in contact with each other, or line segments in space, or curves are contacting each other. That's its own area of research. If you're interested in it, you can do some sort of sleuthing on your own, but it's a long-standing problem that's been around since largely the invention of computational geometry and sort of the beginnings of computer science. But essentially what happens is, on the left-hand side, we have a body. This body is acted on by some force. You might see how this resembles some of the Hertzian contact images we've been looking at. But this body now is discretized into small elements. And we'll call this our contact surface. On the bottom, we have another body. This body is also broken up into elements. And this element has a leading surface called a target surface. These contact and target surfaces then, as they get closer and closer together because this force is pushing them toward each other, what we search for is the point at which these two things come in contact. Well, what does that look like? Well, that looks like one of them bypassing the other. Here we're showing a large degree of penetration where one body has gone completely past the other body, and this happens if we do not tell the program that that's not supposed to happen. If we don't tell the program that's not supposed to happen, then it doesn't realize it, it doesn't try and stop it, and it will push these two things right past each other without applying any contact boundaries. So we got to do two things. We have to have some algorithm that tells this surface and this surface that, hey, you need to look for the point at which you two things are coming together, and then after that, we have to calculate what those contact stresses are. Another thing I'll point out from here is that you can see that, yeah, it could be that our nodes don't actually line up, and so we might have to search for places where a line segment, which generates the surface, crosses another line segment or another node, which generates that surface. And those are the search algorithms I talked about before. So the type of contact in SOLIDWORKS dictates how two parts will interact. And SOLIDWORKS gives you three options here: bonded, allow penetration, or no penetration. So for an example of bonded, what we're seeing on the left is a system of two bars. These are 3D solid generated bodies. They're fixed and fixed, so built in on each side. There's a small distributed load, and then point load or really a line load in the middle here at the end of one and in the middle of the other. And what we see for our solution on the right-hand side in displacements is that where they're fixed, nothing moves. And at the point where they're bonded, we have the same color variation because they're actually moving the same amount. We can also show a solution for another case, a little bit of an animation to see what would be going on. Here what we have is a system of, again, 2 bars built in at each end. We've got a little bit different on our loading condition here, but we can see at the point where they're bonded, they move in concert with each other. The allowed penetration option treats the 2 parts as if they're disjointed. Yeah? The loads are allowed to cause interference between the 2 parts because numerically, as we said before, there's nothing telling the program that these 2 things are actually trying to exist in the same space. Using this option can save solution time, of course, because it doesn't have to check, 1, for whether or not they're in contact, and 2, it doesn't have to calculate any contact stresses. But you should only do this if you are 100% sure that the parts will not interfere with each other, because since there's no checking, there's nothing in the model that's going to tell you when this happens. And so you'll have to see it in the solution, or else it can go as something that you miss. So what are we showing here? Same basic geometry. Now we're pulling up, we're pulling up, we're pulling up. We're still fixed in on our sides. And what we see is that since these 2 things are not working in concert, since there's no connection between them, this one can actually pull away from the other. What else can we show? Well, simple animation. You saw that distributed load on the top, the one on the bottom, the blue one's actually fixed on the end, the other one's fixed on the end. Since they're not moving in space, they're moving relative to each other. But the blue one is unloaded, so it doesn't move, and the one on the right is pushed through the blue one. Again, because there's nothing telling the program that those 2 things are occupying the same space. We haven't told it to check because we've said allow the penetration. So this one will run faster, but it gives us a result that's non-physical. And so these are things you have to watch out for if you use this allow penetration option to try and get your model to solve faster, but you can run into some problems. The next type of contact is no penetration. This is kind of our workhorse for when we have contact problems where 2 bodies are coming into contact with each other. They're not necessarily rigidly mated, as in our first bonded type of contact. This one prevents interference between 2 parts, but it could allow gaps to form. Whereas with bonded, they're completely fixed. With this one, they're only in contact where the geometries are saying that they are overlapping. It's the most time consuming to solve because you have to check for the contact as well as solve for the contact stresses. So we go back to our original configuration, fixed, fixed, built in. We have our 2 small distributed loads. We have our line load in the middle. And our solution shows that, yes, the ends don't move, but we have one body pushing down on the other, and it causes this one to slope downward, and there's our gap because they're not actually touching. If we look at animation, our animation shows something similar. We've reversed a little bit our boundary conditions. This one's pulling up, this one's pulling down. This one moves down a little bit, this one moves up a little bit, and we have this gap being generated between the 2. As I said before, there's a whole history of mathematics that goes into how you determine whether or not 2 surfaces are in contact with each other, and especially 2 surfaces that are discretized by nodes as they are in the finite element method. We won't get into that history, but we will point out one important piece of it, and that's whether or not the meshes are compatible at those locations. What do I mean by that? Well, on the left-hand side, we're showing a condition where we have this component A, we have this component B. Let's assume that these things are meshed, And it turns out that along the surface, the elements have nodes that are coincident. In this case, we have a bonded situation where our mesh is compatible. Why is that? Because the nodes are coincident along that surface. Here on the right-hand side, we have our component A, we have our component B. Because we have component A and component B, these two things were not necessarily in contact to start. They were meshed separately, and because of that, the nodes may not line up. Since those nodes do not line up, this is a mesh that is not compatible, and then interference can occur between our two bodies during loading, and this is what would have to be solved for. Here, since nodes track displacement, we know that any motion of these nodes is transmitted to both component A and component B automatically because they're the same nodes. It's not necessarily the case over here, and so the program has to solve for what happens along this line of the surface as those two things become in proximity to each other, which is why these problems take longer to solve. Okay. So how then do we go about enforcing that concept that these two bodies are not supposed to penetrate each other if we have the no penetration method selected and we're not using something like allow penetration or we're not using the bonded? Well, the way this is done is through either a penalty method or a Lagrangian method. That's what they're called. And remember, the problem that we're dealing with here is we have a surface on one body, our contact, a surface on the other body, our target, and we're trying to make sure that these two surfaces, when they come close together, do not overlap. That overlapping looks something like this, and so then how do we then ensure that, well, this surface does not push through the other one. The red doesn't go through the blue. In SolidWorks, the augmented Lagrangian method is used in static and nonlinear cases. And we'll talk about what that means in a second. The dynamic solutions use a penalty method, and they use the penalty method usually because it can be somewhat faster, but it sometimes is unstable, which is an issue with it. How do you do these force calculations using these two different methods? Well, if we're using a penalty method, that's a pure penalty method. In a very simplified sense, what happens is we assume that there's some spring constant that exists, and that spring constant tells us how stiff a force is going to push back against a body if it is some depth below the surface of another body. So if we have some mathematical representation of where this surface is, we have a mathematical representation of where this surface is. At any point, we can calculate this depth, and if we know that depth, we assign some stiffness to it, and so then we apply a fictitious load on this boundary to push it back to that level. Once it reaches that level, this penetration distance goes to 0, so the force goes to 0, so it should be equilibrated there. Now you can imagine if this K value is too high, then the force that it pushes back with could push us back into a non-contact region that's too far. Or if our solution method generates an increment of a step for penetration that's too large, again, this force can be too high, this F normal, because the penetration distance is too big. And that's where our instabilities come from. An augmented Lagrange method does something like this, where yes, we have this stiffness, yes, we have this penetration distance, and we can calculate some pushback for that, but we also have this extra term. And if you remember Lagrange multipliers from a differential equations class or maybe a Calc 3 class, Lagrange multipliers exist to add terms to a solution that help the solution satisfy some constraint. I won't go too much farther into it than that, but the purpose of this lambda here is to scale this force value such that you get both smoother results, you cut down on the instability, and also you have this surface track back to that surface more efficiently. And again, there's probably 50 years of mathematics behind how that's been done. If you're interested, you can go look at that as well. But just know that the augmented Lagrangian is meant to smooth out that response. But in doing so, sometimes it can actually take longer. The pure penalty method, though, can be unstable because if k is set a little too high or the penetration distance is too high, then it can actually be pushed back too far. Alrighty, so now that we know we've got these algorithms, and these algorithms are trying to figure out whether or not things are in contact with each other, and then once they find them in contact with each other, they're trying to push them back to some level where the penetration depth goes to zero, either using the augmented Lagrangian or penalty methods. We now need to know how to tell SolidWorks which things to look for to be in contact with each other, because there are way too many surfaces to check them all, and so we have to give them, as that figure suggested, pairs of things to look at to compare, or groups of things, group 1, group 2, to look at to compare. We can do this by assigning things to either a global contact group, component contact groups, or contact sets. And each of these have different sort of caveats and different restrictions and different capabilities, which we'll talk about next. So first up, global contact, which automatically makes assignments in multi-body parts. So if you have a multi-body assembly and you bring that thing into a simulation, you begin to make connections and contacts. Here we're showing under connections, component contacts. Global contact is set automatically to bonded. What does this mean? That means that everything is rigidly attached, or assumes it's welded to everything else. And you can see this in the connection folder in the study tree. Some things that will work well for, some things it will not work well for. Yeah? Usually it does this on contacts that are initially touching faces, and does this for all components in the assembly. However, if there's a gap, no matter how small, between the faces, then the global contact definition will have no effect, because it won't bond them together because it thinks you tried to make them separate by making them even 0.0006 inches apart. Be aware of that, because things on your screen that may look like they are coincident may not be, and that's where the geometric relationships in the CAD side of SolidWorks become important. If you have this situation where things that you want to be in contact with each other are not necessarily close enough together for it to find them automatically, then you have to define what's called a contact set, which we'll talk about next. And that contact set essentially puts things into groups and says that this group and that group should be in contact with each other. And in some cases, you'll have to go into this global bit and define things manually if for some reason you don't want to do the contact set. You want things to be across the board for all parts, and you can do that as well just by selecting faces and assigning them to be contacting in the manner you desire. As I said, component contact works between selected components and acts similarly to global contact and how it acts, but not what it acts on. As with global contact, in the case of component contact, the faces of two parts need to be initially touching, yes, and that initial touching bit, you can assign them to be part of a contact group or contact set together. It'll always overrule the global contact condition. So if the global contact condition is set to bonded and you want the two things that are initially touching to do some other type of contact, then you put them in a set and give them the relationship that you want. This means is you can still apply this no penetration contact between some parts in the assembly, even if you have a global situation that says everything is bonded. You just select the two parts you want to have no penetration instead of something like bonded and put them in that set with that condition. And it overrides the global. Okay, so how do we get to this component contact? Well, it's accessed as with most everything through the study tree. So how do we do this? We can right-click on connections within the study tree, and that brings up another submenu within which we can select component contact. Yeah, and then that brings up yet another menu. And in this component contact property manager, under the components, you can select the bodies that you want to apply the chosen contact option. So you can apply this here. This chosen contact option will be applied between all the touching faces of all selected components. So you put your parts in here, and then it'll search out which things are touching, and then it'll apply either no penetration bonded or allow penetration to all of those surfaces. Now, if there's some surfaces on some of those parts that you want to have something different than what you set here, then you will need to apply a contact set, which we'll talk about in a bit. Okay. Component contact, before we get on to component set, also allows an option for a user to specify distance that is considered touching. So remember what I said before. It's looking for things that are coincident. If they're not coincident, however small, then it's going to say that they are not part of your component contact because there's a gap. What you can do, however, in SOLIDWORKS 2016 and forward, is if you have the contact type set to bonded, there's an option that turns up for non-touching faces. And this option that turns up for non-touching faces gives you then a tolerance on how far apart things can be for the program to still consider them to be touching. So things that aren't necessarily perfectly coincident, but you know in your model, with respect to your model, they should be bonded, then you can set that distance here, and it will then go through, find all those faces, and assign them to this contact set, component contact group, and apply the bonded procedure to them. So very useful tool, and it can probably save you a whole world of hurt if things are turning up not to be bonded when you want them to be in your model, because maybe somewhere in the definition of the drawing there was not either a geometric relationship set correctly, or maybe there wasn't one set at all that would have tied those things together. We'll also point out here we have this option of compatible mesh and non-incompatible mesh. Largely, the incompatible mesh option will task SOLIDWORKS with taking the individual parts and doing the interpolations between those two surfaces and between those two meshes for you, so that you don't have to worry about making the meshes in a way that's compatible. It's generally a good option to go with. All right, our final group is the contact set, which allows users to override global or component settings and deal with gaps in another way. So the main two reasons why you should use this contact set are exceptions. If you have this contact set within either a component or within a global setting, you can specify specific things within those groups that have a different type of relationship, whether it be no penetration, allowed penetration, or bonded. So if you want to override something global, you can do it by selecting the faces that you want to override. And if you have to deal with these initial gaps, another way you can deal with those gaps is to just directly assign faces to a contact set group. Directly assigning the faces to that group then tells the program wherever these are going to assume to be in contact with each other and puts restrictions on them. All right, some notes on contact algorithms in SOLIDWORKS. It's a good idea to select the largest face in the bottom selection box, or the faces for set 2, because this face may be meshed with a larger element size, and this can affect mesh compatibility. So when we're defining these contact sets, remember, sometimes it'll ask you to define two different sets. In the old terminology, it used to be one was a master, one was a slave. In newer terminologies, one's your contactor and the other is a target. And in the most recent, sometimes it's just set 1 and set 2. But what happens here is it tries to look for intersections of set 1 with set 2, and the things in set 1 with the things in set 2. And if we are defining set 1 as several complicated surfaces, or set 2 as several complicated surfaces, it just makes the problem tougher. So what we can do then is group the larger body in the faces for set 2, and then the other bodies in the faces for set 1, so that when it tries to find the solution, those ideas of sort of the mesh compatibility, it's just a simpler way for the program to go about it in its solution procedure. Okay, this is an especially important concern for no penetration contacts because, as I said, you're actually trying to look at the intersections of those surfaces. And if your program thinks that the surfaces that it's trying to combine are these large complex things, then what you will have is more difficulty trying to solve that problem. Another issue is to make sure that you define one contact set per reference face. So here we have a face, here we have another face. These things may be coming in contact with other things. They're fixed, so they're not necessarily coming in contact with themselves. But if we define both of these two things as a single face, then the thing that they're trying to contact, the algorithm to try and find that intersection is going to get possibly confused because this face and this face are radically different. They have different normals. They're pointing in different directions, different concavity, all of that stuff. So we just define this as one face. We define this as another face. And then we say separately that they're each in terms of contact looking for this other face to contact. So for example, in this image, one contact set is defined for red, one contact is defined for green. So we keep those two things separate even as we apply them to be in some sort of contact relationship with yet another face. If all these faces were in one contact set, then like I said, the program's just going to have difficulty trying to determine for this complicated group its combination to, or its relationship to another group. So we just make it a little less complicated by saying, yeah, analyze the red one, yeah, analyze the green one separately. All right, to summarize, you can specify global component and contact sets to efficiently define the problem. For global and component contact, you don't really have to select specific entities since they apply to initially touching areas. It will do that for you. Once you select the whole part, it narrows it down to what surfaces are important. The global contact defines the most common condition that you want. It'll apply it everywhere, and then you can override that with component or contact sets wherever you're needed. And you can do that because the component and contact sets override global. Alrighty, folks. Once again, thank you for participating. Thanks for joining in and viewing. Hopefully you've learned a good bit about how SolidWorks implements contact conditions, a little bit about how those search algorithms and how those penetration algorithms work, the sort of penalty method and Lagrangian methods. Most importantly, we have the three types of definition: allowed penetration, no penetration, and bonded that we can deal with, because we have to know how those operate, because those determine whether or not our model is behaving physically. And then that sort of small caveat of the non-touching faces, which allows us to set a distance or a tolerance where things don't have to be exactly coincident, but if they're less than this close, we'll assume they're coincident, which can help us solve some problems of nitpickiness where it'll do it automatically for our whole assembly as long as things are close enough, which can help get past some issues with maybe how we did the geometric definitions and constraints in our CAD model. All right, thanks for watching. Take care, have a great day, and we'll see you next time.